Good evening, everybody. So today we'll look into the amplifier section and mostly the LNA, low noise amplifier part. But before going there, do you have any doubts from the previous class or previous assignment? You can speak out. Yeah, and especially I'm surprised that only one guy has submitted the assignment after 2 weeks. Hello, can you hear me?
Yeah, actually, sir, we have the some problems regarding assignment. Uh,
Okay,
but the
like hmm.
simulation, the क्या बोलते हैं इसको? Layout is sorry. The
Could you do the harmonic balance simulation?
no simulation is not done, but schematic is ready, but simulation is not done.
Not done means what? I mean, did you do the basic schematic simulation? Layout is fine. Okay, layout. If are you getting the results, a good efficiency in simulation? I mean, basic circuit simulation.
No, sir, I have a problem regarding this assignment because I can't understand the schematic is right or wrong, but uh, some
See. Okay. See, problem is, I guess you did not start from the basic. You directly went to do assignment. See, you just first do the circuit what I have shown in the last, the tutorial. You just do the same one and see if you are getting the results. Okay. Then you go to assignment. Okay. So all of you here present here, I will first start. I think like nobody has done here. First, you do the circuit what I have shown in the tutorial. You ditto copy that and see if you are getting results with that. Then you go to the assignment. Okay. Anybody else has any doubt? Any basic conceptual or theoretical doubt? Or like how to do, what to do? Otherwise, we'll go to the amplifier section.
sir, I have watched the video, but uh, till then also I have a problem to do this assignment.
Did you do the circuit in the tutorial? You do that first. Because there you can see the circuit, right? You copy and paste that in your ADS and then you do it. You understand what I'm saying?
Yes.
Okay.
And second
Start.
thing is that
Start.
I have an ATS, I have AWR. I know, sir, you don't know the AWR, but the problem is that I can't find LSSP parameter or something like that in AWR. That's also a big problem with me.
Okay. That's okay. You find out. You have to find out there. It might not be LSSP there. It might be called something else. What about others? Anybody else here are using AWR here? So yeah, Pooja, yes.
Yes, sir. I am using AWR. Yeah, LSSN. It is named as LSSN in AWR. It's in the
Hmm.
after defining ports of harmonic balance. You will
Hmm.
get in the when we are assigning the graph, and then for we have to add the measurement into the graph. There
Hmm.
itself, we have to go to this parameter or that power section. After power
Okay.
section, the power section will split up to some other sections. There you will get into LSSN. So that is
Okay.
named as LSSN, not LSSP, the AWR. As far as I have thought, that is the same one which you are doing in ADS.
Yes. Okay. Yeah. So yeah, and how far did you do, Puja? Yeah, how much could you do there in the assignment?
Sir, I am facing problem. I made the circuit which is given in the paper, but I'm
Hmm.
confused that whether two ports has to be added or one port. That thing I'm
No.
confused.
No. See, this is only one port device because you are harvesting the circuit, harvesting the energy, and the energy will be how will you get? It will be a DC voltage, right? So that is not a RF power. The output signal comes from as a DC voltage.
Yes, sir. I did with single port, but
Hmm.
I'm not sure because when I'm referring some videos related
Hmm.
to nonlinear
Uh,
devices or
no, no, no. See, then I think again the problem is you did not do the basic circuit what I have shown. You start from there. Okay.
okay, okay, okay,
Yeah, that you first do and see the results you are getting similar or not. Then you move on to assignment. Yes.
okay, sir. Okay, sir.
Ah, okay, okay. Anybody else? Okay, so if not, we will move to the class then. Okay, so today and tomorrow is the amplifier circuits and especially LNA design. Okay, so although we'll look into the normal concept of amplifier and how the noise figure comes into the picture, and then we'll see how LNA can be designed. If there can be also a part in power amplifier design that we will not see into this lecture or this course, but it's quite possible you guys can look into one of these books. Okay, so Puzar is what most of this expressions and all we are following here. But there are several other books like the Ludwig and Puzar has another book on RF circuit design, like in RF microwave and RF design of wireless systems, and then this Chang's book on radio frequency circuit design and all. So who are more interested towards the circuit part or like analog design, you guys can look into this. And especially who are more interested in only amplifier design, you can look into the very good book of Gonzalez, Microwave Transistor Amplifier. So that book is only on amplifier. Okay. So you can, the book by Gonzalez, you can follow that also. So if you see the RF amplifier has so many different components, like which kind of particular device or transistor is used, like CMOS or like JFET or BJT, all this. And then mainly in our microwave, our concern is how to how the S parameter is concerned here. Then ensuring stability of the device. Then noise comes into picture, and from there we have the LNA or low noise amplifier. The other concept is non-linearity, right? So there will be like P3dB. At some point, the output power will saturate, right? So there you have this, the power amplifier design mainly focuses on this. So we'll look into mostly the LNA part, okay, and the basic properties of RF amplifier. Yeah. So now see the the main concept we have been so far using in all our RF circuit design, what was it? Is like is the impedance matching. What we are looking from or getting from SO11, right? So impedance matching is it ensures that almost all the power goes into the circuit. There is very less amount of reflection. So that happens only when your input impedance is real. That is what you have to understand. Or it might have some complex part, but that is insignificant. Okay, because we do the matching in terms of a 50 ohm load, which is real. So Z in minus Z naught, what we do by divided by Z in plus Z naught, which is the formula of the gamma or reflection coefficient, takes care of the Z in the input impedance. So far mostly we have looked into except the power circuit or the energy harvesting circuit where it was complex because we are using a diode. But if there is no diode or active devices, then you will have a real part only. Okay. But now, the more we are going into these nonlinear devices, they are almost never real. Okay. Obviously, so they have some capacitive element, some inductive elements, all this comes into picture because of nonlinearity. So your input impedance or load impedance, both cases are active. That means it's not at all real. So then how can you match it? That is a concern. The impedance matching does not work as usual, right? So then what are the other options? what kind of design, or like how should be our approach towards the design there. So what do we need in amplifier design? So in case of LNS, we want noise, reduce the noise so that the minimum detectable signal can be improved, right? And towards power amplifiers, we want to reduce the non-linearities. So, the up to large signal can be amplified, okay, reliably replicate the input. It on the saturation point will be even further more, so that the non-linearities are reduced there. And these are the main performance conditions for the active circuits, right? So noise and non-linearities in case of, especially in case of amplifier design. So now we have to look into see how we can design these things, but we will mostly focus on, focusing again on our strong part in microwave, which is S parameters, and we'll see like how Smith chart comes into picture for design. So I will ask all of you to again go through the basics of Smith chart, because all these designs heavily reliant on Smith charts. You'll see that hardly you can do all this on pen and paper. Mostly these are like graphical analysis, which is done through Smith charts. Okay. So now in case of amplifier, let's see the basic block diagram. Okay. Let's say the block diagram inside, which has a S parameter given, right? It's a black box, let's say. And at the input side, it is connected to some source with a source impedance ZS. And at the load side, it is connected to load. Okay. Now notice here the different parameters, which are very vital here, because all through the amplifier design everywhere these parameters will be used. Okay, so this is very vital how we define these different reflection coefficients, which are defined as, you see, the first one is gamma s. So gamma s is looking towards the source, is the reflection coefficient gamma s. Gamma in, at the same point you look towards the device itself, so it is the parameter of the device. Okay, your, in this case, maybe the BJT. Okay, that is gamma in. Separately at the output side, you see this is gamma out, which looks into the output port of device. So again, it is a parameter of the device. But gamma L at this right side here, this looks into the load. So this is the reflection coefficient due to load. Okay. So now why all these different reflection coefficients are required? That comes from the moment it becomes the input impedance or the load impedance become active, or like it has some complex parts, we no more have a we no more interested in the reflection coefficient alone. We need to also look into the maximum power transfer. And now if you here look here, the these are two very defined concepts: maximum power transfer and the reflection coefficient. The reflection coefficient becomes zero only when Z out is ZL. Let's say the load side, we want to reduce the reflection. Okay, we want to have the matching at the load side. So simply we want Z out is ZL. So Z out is the output impedance of the device, and ZL is what it is connected to. So simply, the gamma formula is what is Z out minus ZL by Z out plus ZL. When you do that, the reflection coefficient becomes zero. And you remember always that this reflection coefficient is determined in terms of incident reflected, the ratio of reflected and incident voltages, not power. Okay, so these are obviously through what we measure, or what is important for us is defined in terms of voltage. So that becomes zero, or this reflection coefficient becomes zero only when Z out is ZL. But as you know from all the basic network theory itself, but maximum power transfer does not happen in that case. It happens when we have conjugate matching. That is, Z out is ZL star. So at the load side or the output side of this device, it depends on how much power, how much impedance you get at the output and what it is connected to ZL when they are conjugately matched. Now this conjugately match comes into picture only when this Z out and ZL are not completely real. If it has some imaginary part, that is what we are all talking about now, right? So then this matters. When it becomes real, Z out and ZL both real, then they are all matched as well as power transfer both happens. But now in this case, it does not happen. Okay, so together you don't get maximum power transfer as well as zero reflection. Now we have to do something else here. Okay. So this, the gamma S and gamma L, uh, uh, the the equations, characteristic equations are given here. This gamma S and gamma L, how you define. So ZS is the source and ZL is the load impedance. And similarly, Zin is the input impedance of the device, and ZL and Z out is the output impedance of the device. Is this part clear? Because this is the basic fundamental, how it is different from the other circuitry or other devices, other like power divider or a filter, what we have been looking so far, how it is conceptually different. So basically, if you see here, so this conjugate matching will happen when Z out is ZL star. So this comes to here, gamma out will be gamma L star. Okay, that will be at the load side. And similarly, input side also, Z in is ZS star. If that happens, you will have input matching. Okay, and that boils down to gamma S equals gamma in star. Okay, so that is what we will use so far. Will throughout this amplifier portion. For conjugate matching, we need gamma out equals gamma L star and gamma S equals gamma in star at both input and output side. Okay, so now that these are defined, what are the other or what are the defined parameters we need to look into or we need to know for the amplifier design? Now see, as I told you, with the active device itself, we can't have both matching as well as power transfer. So what do we do now? So now here comes into picture a matching network. Even in the previous case also, if you remember, we have used the same concept. So because the network itself cannot be matched, we need another network at the input side as well as the output side. So we'll have an input matching network as well as the output matching network, which will ensure both matching as well as a maximum power transfer. Now see, now because of this, see the schematic at the bottom. This is the active device in between, inside. Okay, so that's like it can represent a MOS or a BJT or define or any kind of HEMT, any kind of active device which will be used for amplification. But now what else are there? At the input side, we have source, which will let's say a arbitrary waveform generator or a VNA. But now we have a input matching network. Separately, we have a output matching network and load at the output side. So as you see, this whole thing comes together. Only active device will not do anything. Only connecting a BJT will not give you anything. So they will run into a lot of problems. That's why the matching networks are required. So for that, you see that we have defined lot of different power terms. One is the P in. What is the input power available from the source itself? And then the other term is called available input signal, which is also called this is not PIN, this is PAVS, available from the source, which is going into the matching network. These two are not same. Why PIN equals not PIN is not equals PAVS? Because here you might not have conjugate matching. Then some power will be reflected, obviously, right? Only when you have conjugate matching satisfied here by the input matching network, then only P in becomes PAVS. That is what is said here. This is very simple. And then because of the input matching network might have some loss, so actual power delivered to the device is something else. It is PND. It might be less than this PAVS. Similarly, actual device output signal is PAD. These are just different power terms, but it is required. You see, because they go through multiple different networks and it might change. And in the output of the matching network, it might go through some loss here. And what we have here, PAO, or available output power. And what is ultimately delivered to load is the output power, PL. Okay, actual power delivered to load. Now again here, this available output power and load is defined. Why? Because they might not have conjugate matching. Only when you have conjugate matching, maximum power will be transferred and it will become same. Okay, that is what is said here. So these are the defined terms for how we use, and and ultimately they will be used to define the gains of the amplifier circuit. Is it clear? Okay, so I suppose either you are understanding all or not understanding at all. So okay. Hmm. So now what comes? Finally, what we want is a good gain from amplifier, right? Other than the noise figure that will come to later. So now how there might be different terms of gain, because you see we just saw at different points we have different powers. So which ratios you take from which one to which one will define the gain, right? So a very simple definition of power gain would be just take PL and Pin, what is given from source and given to load. Okay, power dissipated and the power input. But now you see it does not take into consideration the inside, what is happening inside, because of matching networks and all. It does not ensure impedance matching. So that's why it is not very important or not very useful. What is more useful is this gain. Definition of this gain is called transducer power gain, or this is not GA, sorry, this will be GT, G subscript T. Okay, transducer power gain. So this is what you will actually find in the datasheet of the amplifier. Okay. So now you see this is defined as PL divided by PAVS. AVS is here. What is the power available from source and what is the power given to the load? Okay. Power delivered to load divided by power available from source. Now obviously see it depends on both ZS and ZL, because here at this side it depends on both sides, source and load matching should be there ensured. S11 S22 it will all play into this. Okay, so that's why this is the gain actually matters. It takes care of the defined matching and other considerations. So yeah, this is PL divided by PAVS, the power available from source. And the another definition is available gain. So this takes as PAVN by AVS. Okay. So power available from network and power available from source. Okay. So together. Now you see it has two conditions to satisfy that. This is called GA, available gain. So available from source is what? This is the P in only when gamma in equals gamma star satisfied, conjugate matching happens, then only PAVS becomes P in. Otherwise, it won't be same, right? It will depend on the matching and all other considerations here. This is the PAVS here. This the top arrow. And this is the PAVN, the power available from network. So which is like it says, which will be PL given that gamma out equals gamma L star. Output side also, if conjugate matching is satisfied, then only the available from network will be same as PL. Otherwise, they will be different. Okay. So assumes this obviously it assumes conjugate matching for both input and output. So we will mainly consider these two definition of gain: available gain and transducer power gain. Transducer power gain is mainly important. Now you have to remember the source and load are external, and what you get from the market as a LNA has these three components inside embedded. So If you want to design a LNA, you have to design all three together: input matching network, active device, as well as output matching network. If you do all three together, a composite design, that will make a LNA. And that's why, the actual output terminals will be here as well as here. Okay, input side and output side. Okay, so these are the just simple two-port network, how S parameter is defined in terms of incident and reflected voltage coefficients. This you know already, I am supposing. So this is the gamma in V1 minus V1 plus. So now there are a lot of calculations of, given the input side how much voltage you are feeding and the load side how much voltage you are getting. So from that you can calculate these gains. Okay, especially the powers. What will be these powers at defined junctions? All these defined powers we have defined, and from that we are calculating the gain. So these you can find in the poser. So finally what we are getting here, you see, these are these defined gains. Okay, all these gains we are defining. So power gain is what we have defined, but that is not very important. Now available and transducer power gain. Okay, now you see they are different. You see, available power gain, it has this S21, 1 minus gamma S, gamma out, all these things are there incorporated. And transducer power gain is even more generalized form. It has gamma S. It depends on gamma S. That means source side reflection, gamma L load side, and then it has gamma in also, S22 also. So now see the amplifier. So for an amplifier, how much gain you get? Okay, this transducer power gain, it depends not only the S21, but also the everything. Gamma S, gamma L in load. So matching is also important. Now you notice, right? Why we are all talking about this defined reflection coefficient? Now because everything comes into picture when you calculate this transducer power gain. What is the important power gain we get actually? What will be referred in the data set. Now there will be a simplified version of this, which is called unilateral power gain. Okay, unilateral means generally active circuits are not reciprocal, right? To remember, we had the basic characteristics of S parameter where we were saying S21 equals S12. That means it is reciprocal from this port to that port, and otherwise vice versa was so far equal for passive circuits. Okay, but now for active circuits, as you know, they are not reciprocal. So that's why you can call them bilateral, right? But now if you can want to have a unilateral case, like let's unilateral means only S21 we get, but S12 is 0. Okay. So in that case, what happens? Gamma in becomes S11. So gamma in, this formula will be here. Okay, that depends on the, you see, gamma in is the input reflection coefficient that not only depends on S11 here, but also depends on all these other parameters. So when S12 is 0, gamma in becomes equals to S11. Okay. Now we can do S21 also 0, then also S11 will become gamma in. Now can you tell me why S12 we are making 0, not S21 here, so that gamma in becomes S11? Yes. Anybody? Is the question clear? Are you with me or not? Hello? Hello?
Yeah, could you repeat the question once?
Yes. So I am saying here in this, this is the expression of gamma in, right? Gamma in is the input reflection coefficient of the device, which
Yeah.
is related to S11 and these other parameters. Now we are saying if S12 is 0,
Mm.
then we have gamma in equals S11. That is
Yes,
what
one
is
one.
written. Now
Yes.
I'm saying S21 also can be 0, then gamma in becomes S11. Why S21 we are not making 0? Instead, we are making S1 to 0. Why?
Mm.
Why S21 is important here? This is very basic.
Sir, because that is a gain quantity, S21.
Exactly. Because we are making an amplifier, right? So
Yes.
that will ultimately give you the gain what you want of this BJT or MOSFET. The S21 will define that. Okay. Right.
Mhm.
And we don't want a reverse gain. That we want to cancel. That is what is given by, that is the essence of S12. That's why we want a very good BJT or MOSFET which have almost close to zero S12, but S21 will be maximum, right? Yeah. So that is all about. See, all these equation expressions will be lot of them, but you have to understand the physical parameters what they mean. Okay, so that is what I wanted to tell you, because otherwise it's very rigorous in mathematics and all lot of expressions and all. Okay, so that's why it says unilateral power. Unilateral means there is no reverse power coming from the output to input side. That is S12 is 0. Then only gamma in becomes S11, and that if you put in this expression, you get a simplified version, GTU, unilateral transducer power gain. Okay, but generally if you see the market, what the devices we get, it will have some S12. It is not exactly 0, but it will be minimal. So now you know the minimum you can get will be better, right? But mainly you see all these expressions, what is mainly dependent on S21 square. That is what is actually defining the gain. After that, this gamma S, S11, all these are coming because of the matching constraints. Okay. So all these things, actually it means how much gain your device gives. This is the intrinsic parameter of the device, S21, but will also depend on the matching network. So that's why gamma S, gamma out, all this comes into picture. Okay. So that's why the what your device can provide, this S21 square, will not be completely given to the load. So there will be some losses here and there, some mismatches. That's why these different terms comes into picture other than S21. Okay. So now you see this is the whole schematic. So inside you have the transistor, and this side is source matching, output side is load matching. And the gamma S and gamma in, how it is defined. Now gamma S is looking into the matching network, okay, not into the source side. You have to see gamma S and gamma in is defined between the input side and the matching network between them. If you look into two defined sides, you notice the arrows here, okay. And similarly, gamma out and gamma L are defined at the output side between the transistor output and the load matching network, okay. So based on this, four different reflection coefficient, your transistor gain will be defined. GT is the transducer gain. And actually, if this overall transducer gain is can be defined into three different terms. You take S21 square is the GAO, and GS and GL. These two parts are comes from the source and load side. Okay. So this is nothing but dividing this whole equation into three different parts. That is called overall transducer gain. Okay. So if you just multiply these three parts, it will come. So always keep in mind this picture. Okay. This whole picture is required. Because transistor, two matching networks, and source and load is always there. Now the first consideration of transistor is, or like consideration of for amplifier is stability. So as you know, we want amplification, right? Right. So there are always, if you remember, two parts. They will be like defined conditions where it works as amplifier. It can always go into a non-stable part. What happens in this? What happens if you don't have stability? It can become like a oscillator. That is what we want to want to stop it. Okay. We don't want to act like a oscillator where it becomes like a non-stable. We want to have it amplification, okay, have it amplifying the signal. So that's why stability is very important in our case. Now if you know in which cases your device will have stability from the basic circuit or diode what you have studied before, can you tell me what are the parameters of your device will tell you that it will be stable or not, it will oscillate?
Poles and zeros.
Poles, yeah, body plot.
Poles are zeros, but poles, if you know, it is actually mathematical characteristics, not a physical. What are the physical parameters?
Feedback.
L and C.
Sorry, what? LS?
Inductor and capacitor.
Inductor and capacitor will tell you, but inductor and capacitor, if your network has only, it will act like a resonator, right? What else? What else will tell you? It will act like oscillator or not?
Like a negative feedback for controlling.
Feedback, see, feedback is again not a parameter, right? Feedback is a system. What ensures that negative feedback or positive feedback for oscillation, let's say? If you remember, I will give you hints that in the basic semiconductor devices, which generates a oscillation. You know, we used to use, we not use, we still use tunnel diodes and gun diodes, right? To create oscillation, which actually creates the RF, acts like a RF source. What is the special parameter they have? Compared to the other diodes
Negative
that
resistance region.
exactly right. So they have a negative input resistance, right? So that is their parameter, right? Yeah, right. So now my point is this, even in this case also amplifier or any diode, they will go into oscillation. This is actually wrong. This positive is wrong. It will be negative. So when their input or output port impedance will be negative real part, okay, they will be actually what we told. It will be a complex in their case. In these cases, their input impedances are not real, like passive devices. So they will have a complex impedance. Now the real part of complex impedance is what? The resistance. That should not be negative. That has to be positive. Okay. So this will be like this will be negative. They oscillates if you have a negative part. Now if you actually look into the equation of gamma in and gamma out, which says z in minus z dot and all. So if that has a negative real part, that boils down to, if you expand that equation, it gives you gamma in must be greater than 1 and gamma out should be greater than 1. Now you tell me a Smith chart, which will be gamma in greater than 1, amplitude of the reflection coefficient is greater than 1. Which part will be in Smith chart? Yes, anybody? You have seen Smith chart, right? Tell me in which case the reflection coefficient magnitude will be greater than 1. Yes, anybody? What is the value of the gamma value amplitude at the boundary of Smith chart? What is the value? This is the basic, right? You must know this. And Smith chart you have already seen also.
Gamma equal to 1
Gamma equal to 1 where?
at the boundary.
And at the center?
Center gamma equal to 0.
0.
0, right. So that's why you see whenever we want a good matching, we want the gamma at the center, at should be around the center of the Smith chart. If it is very much expanded, that means is like it is the reflection coefficient is not 0. We always want good matching means it should be at the center. Now here what we are more concerned is the boundary. Boundary is gamma equals 1. If you go outside Smith chart, that we never go. You remember now. We always do all the calculation inside Smith chart. Now it is time to go outside. Why? Because that is the boundary which says gamma greater than 1, amplitude of gamma greater than 1. So now you are obviously thinking, no, what is that? Because we always do, because we always work with passive circuits. Mostly we are concerned about passive circuits. And passive circuits does not give you amplification and these are stable. So that's why they stay inside the Smith chart. Now here in the amplifier case, it goes even outside Smith chart. Okay. So there only you have the Here, if you see, that region actually it defines the oscillations part or non-stable part. Okay, so now we have to ensure that we don't go into that zone. We have to ensure that we stay in the stable zone. What is stable zone across the according to this? It must be gamma in greater than 1 and gamma out greater than 1. Yeah, who is here? Okay, so now there must be two conditions. One is unconditional stability. Unconditional means you don't have to impose any condition. That will happen only when gamma in greater than 1, amplitudes of both out, in and out are less than 1. That means you stay inside Smith chart. This happens for all passive source and load impedances. That is for all gamma is less than 1 and gamma L less than 1. Okay. See, the source S and L is depends on the source and load side. Okay. So it depends on that. For all different cases, always you have in and out less than 1. But now this might not be satisfied all the time. Especially in our case, you will see it never satisfies almost. So that is why we are more concerned about what is called conditional stability. So that gives amplitude of gamma in and gamma out less than 1 for some selected cases. Selected cases, who will select that? For some cases of gamma S and gamma L. Now we have to see what are the ranges of gamma S and L. That means into source side and load side. I mean, in source and load output side, if we look into, they will impose some condition only for those gamma S and gamma L values. In and out will be less than 1. This range we are more interested where we have conditional stability. See, this is the expression, right? We finally want gamma in less than 1, gamma out less than 1. Both of them has to be less than 1. Then only it will be stable. Now this table comes without any condition. That means there is no condition on gamma S and gamma L, or with some condition that gives you conditional or unconditional. We are more interested in conditional stability. So we have to evaluate what are these values of gamma L and gamma S, which will ensure this gamma in and gamma out less than 1. Okay, so for that now we'll go into some calculation based on Smith chart, or not calculation, analysis. Is this part clear? So always remember gamma in and out. These are the parameters for the device itself, input and output side. And gamma S and gamma L will be defined by the matching network and the other things. Here again you look into this. Gamma in and gamma out here. These are coming from the transistor itself. And gamma S and gamma L will be defined by the matching network. Okay. Now what we want to this device to be, to be stable in and out, gamma in and out has to be less than 1 both. And for that, not only for that, we will have some condition on gamma S and L. Okay. Now we'll see which are those conditions. Now the interesting thing is, if you notice here in the first expression here, gamma in depends on gamma L. Input here depends on gamma L. Input depends on the output side reflection. Why? Because these are, again, you always remember, these are nonlinear and active devices. Input depends on output side, output depends on input side, because these are nonlinear. Okay. So now that's why if we actually, we have to now, what we want to calculate is what are the values of gamma L and gamma S that will satisfy, or that will lead to gamma in less than 1 and gamma out less than 1. Okay. So this equation, this one and that one is we want to solve. From this, we get some, we get some considerations. We'll go into that now. Okay, so the limit of stability is from the first condition, this should be less than 1, right? And the limit will be if we take equals 1, that is the limit of gamma in. Okay. If we take that, and if we expand this, finally it leads to expression like this. Leads to gamma L, some value here and some amplitude here. Now can you tell me what is this? This is the equation of what? You are having an expression for
Circle.
gamma L. Yeah, it's a circle. So for this circle, this is the center and this is the radius. This circle, how do we plot? We generally plot in Smith chart. Okay. Now see, you remember this is called the for output stability because it will actually define gamma L. Okay. But this comes by gamma n equals 1. From this expression only we are getting. So see, output stability depends on the gamma n value. By making gamma n equals 1, we are getting this expression here. So that is why gamma L circle will make equation circle here. This is the red circle. Okay, this is the gamma L circle we just got. Depends on S11 less than 1 or gamma in less than 1. Okay, gamma in actually it will define this gamma L. Okay, because that is how we are getting here. So this load side stability circles, this is called load side stability circle, where we get some center point here, some radius out defined by this expression, and center is by this. This will give us the condition for stability. How? See, this region inside it, this is always gamma n less than 1, right? So gamma n already we are plotting on gamma n circle, gamma n Smith chart. So we know inside the circle is stable. Now this one, the load circle what we got just now tells that inside this is the non-stable part. Inside this circle is the non-stable part. So now from the intersection of these two circles, what do we get? What is both outside this and inside this? That is what this green zone is. So this means this green zone is defining where is the stability. Where is the stable part of this device. Okay. This is for the normal Smith chart. Okay. Now there can be also a portion where S11 is greater than 1. Okay. So there all these things will get reversed. It will be inside this and that will be outside this. Okay. But we need not go into this second circle. You stick to the first one only. This is simple for analysis. First one is this is load side out stability. Okay. We are defining load side because gamma L defines load. This is the center circle. Uh, Inside this circle is unstable part. Outside is stable. But now outside we cannot take anywhere. Outside we want to take only this side where even gamma n is also less than 1. Okay. So this portion, green portion is the uh, output stable part. Okay. Out from this stability circle. Similarly, we can also get a stability circle for source. Okay. So here you see we are getting all this from this expression. So similarly, if you do get from here, you get expression for gamma s. This will give you source side stability. So you will get a similar center and similar radius, and your expression will be something like this. Okay, just it will get reversed. It will be a gamma out circle here. The big one will be the blue circle. Smith chart will be gamma out, and your red will be gamma s source. So it will be exactly similar. Okay. So what it means that you need to do two different Smith chart analysis for stability at the input side as well as output side. By drawing this Smith chart and looking into the intersection will give you which are the regions where both input and output side is stable. That means it does not go into oscillation. Is this part clear to you? Okay. So, okay. Now these are the same thing what I showed you. So many cases it's not possible to make it unconditioned stable, but there are some additional things you can do to your BJT, like you can add a added input impedance here, source resistance here R in, and also in parallel you can add another one, right, RG in conductance. These can make you give you a better stability. Why? Because let's say it is unstable. Okay, so that means from just conceptually, intuitively thinking, if you see Z in here has some negative impedance part. Now, if you just add a positive impedance here, that can lead you to it can just reduce the negative part, right? So that is what you can do. But the problem is if you add a input impedance and admittance here, it can reduce the gain. Okay, so that is one part, but otherwise you can make it unconditionally stable by adding some input impedance. If you are willing to trade off some gain, you can get stability. Now, all this analysis we have done, this is for understanding, right? But is there any test for stability? Yes, there are some simple test which is called k delta test or Rayleigh conditions. Okay, so these conditions tell you this k, it gives a k value and delta value. That's why it's called k delta test. It has some defined, it is in terms of S11, S22 values. If you see, if k greater than 1 and delta less than 1, if both of them are satisfied, then only it will be stable. Okay, that is has to be for stability test for any device. This S11, S22 values will be given in the data sheet. Okay, so from that, first thing you have to do is that is this k greater than 1 and delta less than 1? If both of them are satisfied, then only they are unconditional stability. So many cases you will see it is not happening both of them together. So then they are conditional stable. That is where all the designs come into picture.
Sir,
Yes.
is there any generic formula for stability? This is for two-port network.
Yes, this is for two-port. This is not for two-port network. This is for amplifier. We are talking
There
about
is
amplifier design. Yes.
amplifier is a two-port network, right?
No, no, no. Amplifier is a two-port network, but there can be thousands of two-port network. We are not generalizing here. We are only discussing amplifier.
But for stability to find, is there any generic formula?
Yeah, it might be. You have to look into there. You look into a control theory book. They will have multiple chapters on stability itself. Okay. So you will have Nyquist plot and Bode plot, all this. You have to look into that. So better, I will suggest you look into a network theory, control theory book. Okay. So now coming back to this, for this amplifier, we have a K delta test as well as mu parameter test. So both of them works good. You be satisfied, then you get a good stable or unstable. You will get from here. Now, what is our main consideration in this is how to design the matching network, right? Once we do it is not stable, we have to do the matching network. So we have to simultaneously have the conjugate matching in the input side as well as the output side, right? Then only when the conjugate matching happens, then only we will ensure that the maximum power will be transferred. So from there only doing this, we get the k delta and this value. This is the expression of k. Now the thing is, many of the cases we'll see device is not unconditionally stable. So we'll do the Smith chart analysis, and from that, what we need? We need to see the possible values of gamma S and gamma L, and this see what we are getting. From this analysis of this Smith chart analysis, we will get the values of gamma S and gamma L because those are the conditions. Only for those values we will get the analysis values of the matching, because that will lead to ZS and ZL. From gamma S and gamma L value, we can calculate ZS and ZL, and based on that, we will design our matching network. Okay. First, we will look into the stability. From there, obviously, most of the cases we will get conditionally stable. And now from this matching network, now from this boundary of this, S parameter here, this Smith charts, we know what are the boundaries or what are the points of gamma S and gamma L for which it will give matching. Okay. Now for that, we'll define our ZS and ZL because gamma S and gamma L gives you source and load impedance, and you have to design your matching network according to that. Now, yeah, one more thing is, you see all these circles and all, it depends on S11 value, right? Now S11 is a frequency dependent parameter. So all this so far we are designing for only one single frequency. Okay. Because all these are dependent on frequency. If you go to some other frequency, it does not ensure that it will match in there also, or it will have stability in there also. All these are frequency specific conditions. Everything we are doing so far. So it does not guarantee a bandwidth. It might be, might not be. So there are the defined conditions or defined, based on the gain, how much maximum gain you can get. Previously, what we have seen is the generalized gain formulas. But now, based on the stability, we have more sophisticated parameters of gain. So one is unconditionally stable. When k is this value for k delta test, if it is greater than k, so then we get GT max is given by this. Transducer gain maximum, which is given by this. But most of the cases it is conditionally stable. That is k will be less than 1. In that cases, we what maximum stable gain we can get is called this. Is given by simply S21 by S12 amplifier ratio, magnitude ratio for unconditional device, GMSG, maximum stable gain. This is a very important parameter. Okay. Because that is what we finally deal with, unconditionally stable device. Okay. Otherwise, the main gain, what you see, we have seen so far like this for unilateral and for this G is non-unilateral devices. But that after further considerations for stability, these gains two. It gives two gains for condition stable and unconditionally stable. So if you have to even decide for some bandwidth design and all, you want to have um, design for a specific gain, but you want some bandwidth also. There are also some defined uh, approach to design. There people define a assumes to be unilateral and have a figure of merit called unilateral figure of merit, which is defined by this, and they impose a condition between this for which values it can be done. So far, that is a defined consideration. So that is also possible. You know you have some trade-off there in the gain, but you want some bandwidth. Okay, that is also possible through this consideration. Okay, so now coming to the important things that we have. We need a matching network. Okay, that can be done through lambda distributed, as we have seen in the same previous case also. Okay, we can do matching in both ways. And then when you have matching, first you look into stability, go into matching, and then we'll look into the noise figure parameters that we are coming to later. Now you see the thing is whenever we have a lamped parameter, we need to do EM co-simulation in ADS. Okay, so that we'll see tomorrow. But many of the cases you will see it will not be possible to only with transistor microstrip lines. You will need lumped components. So it will need to both layout simulation as well as co-simulation. So there are different kinds of amplifier discrete transistors available. Like you can use RF CMOS and LD MOS, and even HEMTs are very widely used, like GAN or gas devices. They are also useful. Okay, so summary is this. We need a conjugate matching here, and for impedance matching, that's why we need adding a matching network here. And then we look into stability so that device does not go into oscillation. And finally, we have to, trade off with some gain, how much gain we want. Based on that, we design there. Okay, maximum possible gain we can calculate. And now, what are the different ways of matching circuit? This is, very simple. You can just take a LC based. The most simplest one is just having a inductor and capacitor based circuit here, right? You have seen before also. Even inductor, these are many different topologies possible. So how you use it, that depends on the input side and the output side, how much is the source and load impedances. Here if you see this example, the antenna side you get, let's say, 75 ohm plus J15 impedance, and you have to match it to 150 plus J75 impedance. So in between this parameter LC here, its task is to match from Z here to Z here, this side. Okay. So you have to do, see which topology is feasible here and values you have to choose. And the mainly what we use, very useful to analysis in Smith chart. I have shown you previous case also. In ADS itself, it has a tool where it shows how you can do in a Smith chart. See, let's see, this is the ZT here. Okay, this is your antenna side gain, what you are getting 75 ohm. But you have to match it to, let's say, 50 ohm. How do you get? So in Smith chart, you see there are multiple circles. So this side, these circles here, you get what is called impedance circles, and the opposite is called admittance circles also. Okay, both of them are possible. You can change by impedance or admittance, both. Now let's say we are using these circles here. This is nothing but, it can be said as admittance Smith chart. See, simply you can go from here till here. Okay, just see how they are, how simple and powerful this tool is, Smith chart is. You have to come from this point here, ZT, to here, because this is where the 50 ohm is, right? That is what is your target. How do you come? You come here from here by this circle, and then come from here till this point till here in this circle. What is this? So first is, how do you go from here to here? You just add a admittance. Admittance comes from here, adding a parallel capacitance. That is leads to here till here. Now you have to go back to this circle. So that means you are adding some inductance. This circle, if you see it moving to a forward, it means adding a inductance. That is why you add a series inductance, which leads you to this. But there might be many other combinations. You can go from here to here and then come backwards. That is L first, C last later combination. Okay. So these are the different combinations you can do in this. And all these are, very much analyzable in Smith chart itself. So I'll suggest just go through this and you will understand. Okay. So these are the previous one was the very basic circuits, but you can even go through, even a complicated one where you can make a low pass, band pass, or high pass network, and that will give you maybe a wide band analysis. Okay, it's possible to have a more wider matching. Okay. So these are the different, stop matching and microstrip line matching, T or pi network possible. Okay. And the other thing also far we are doing talking about outside now. Now, you see, BJT, we are talking about S parameter analysis. That is nothing but small signal analysis or RF signal analysis. But how are you going to, work BJT in your desired mode? That for that you need a biasing circuit, right? And if you remember, even previous case also the diode and all, we had a biasing network. Here also similarly, for your device transistor also you need a more sophisticated biasing network. Here you see you have RF chokes, capacitors, blocking capacitors, and all this. These are all required because your transistor will have multiple ports, right? So in source side as well as load side, you need two biasing networks. That is what is done here. And even you can have different common emitter, common base topologies available. Even this is for the FET and all. These I guess already. And this is the complete circuit what you get. Okay. This let's say is the BJT or what is the actual discrete parameter we use inside. Then you have a input matching network this side, output matching network here this side, and then you have a input side biasing as well as output side biasing. This is the voltage sources, and it has chokes, even capacitors, all this together. So this whole thing might come inside a package. What you get from a market is the overall LNA amplifier design. Okay. So our task is to design. We take a discrete BJT or transistor from the market and design the rest of the parts, matching network and the biasing and all, so that we get the LNA gain. Okay. So this is so far done. Any question? Otherwise, we will go to the now noise part. Any question here? So yeah, whoever, many of the people I guess will be starting first time on amplifier. I will suggest you start from Pujar, and who are more interested into very in-depth analysis, look into Gonzalez. Okay, this book Gonzalez is on the transistor amplifier itself. So is there no doubt? So then we'll move to the next one. Okay, so now coming, we have seen so far the amplifier design. Now the noise part also has to be considered, right? Because we are talking about LNA design. So first thing is, what are the sources of noise? So very basic part, or the most fundamental part of noise we have seen, even I guess you also studied in UG only, which will be the thermal noise, or also called Nyquist or Johnson noise, which depends on the resistor and the temperature the resistor is in. That will give you the that will lead you to this thermal noise, right? And the power spectral density is defined by this SF is K into T. The T is the thermal temperature of this device, and K is the Boltzmann constant. And there might be other noises and all, because the amplifier, as you know, is a nonlinear device. It might have the 1 over F or the pink noise and all other things, but mostly, and Poisson noise and all, mostly we will consider into thermal noise, because that will generally will lead to the significant part of it. And the noise power, the Rayleigh formula gives you this V square by 2n. V square is the noise power, noise voltage. Okay. And it is simply given by KTB. K is the again Boltzmann constant, T is the temperature, and B is given by the bandwidth. Okay. Now device, this is the absolute bandwidth, not the 3 dB bandwidth of device. Total how much bandwidth this device has. Based on that, this noise will be considered contributed or calculated by this. Okay. So simply, if you see just these four things you must have studied before, we will not go into this. A noisy resistor can be expressed in terms of voltage, noise voltage and all. And if you have multiple noises or multiple noisy resistors, they are not added in simple series. It is RMS calculation. Okay, Vn square plus Vn2 square. And similarly, you can add multiple components like this. And the noise power, as you know, sorry, calculated mostly noise power will be given by the bandwidth of the device as well as the thermal temperature. Okay. Now, a very important characteristics of the noise parameters is equivalent noise temperature, ENT. Okay, equivalent noise temperature, which is simply it tells you what is should be the effective temperature of a resistance, let's say, or the source noise source, so that that will lead to what just by putting that into the formula you can calculate the noise power. Okay, so this white source noise is replaced by a resistance with equivalent temperature T, that will lead to the same noise temperature NO, sorry, noise power in naught. Okay, so this is that T is nothing but N naught by KB, this ratio. So you can replace it by a effective resistance, effectively with a resistance. So it says if you don't have any loss in your device, like say antenna, so how this noise will be coming? Where is this noise coming from? Let's say there is no noise in your device itself. Let's say for antenna, so it will be coming from outside. So even it is said, cosmic background radiation can lead to a noise of around some noise, which will be equivalent to a temperature of 3 Kelvin, only 3 Kelvin. Okay. So obviously now you can understand how less significant it is. Okay. And now, and generally we work at our room temperature is around 300 Kelvin. Okay. So this 300 Kelvin as this 3 Kelvin, you see 300 times less. Now, obviously, so if you use all these devices in this room temperature, that will lead to lot of noise. Okay. Because of this 300 Kelvin itself. And if you want something, to be very less significant to noise, which is very sensitive to noise, what do you do? we generally, what we do, we cool it down. Generally, if you see all the uh, significant devices like quantum devices and superconductive devices, they all works in very low temperatures, where this noise will be so less. Okay, that is the one part of consideration. We want to reduce the thermal noise. So that happens only when you work in a very low temperature, like a super cool temperature. That noise will be gone. So this how you can calculate, the more consideration is, let's say your G is your device, or let's say your amplifier. So input side, let's say there is no noise coming in, but output side you will have some noise because of the amplifier, right, itself. So how you now replace this? It says now it input side only, you make this register here with some equivalent temperature with N naught by GKB. Okay, and then now we replace this noisy amplifier with a noiseless amplifier. So that leads to this gain will be amplified. Okay, see why GKB? Because this noise here at the input side will be amplified by G, and finally you get the same NO. This is just a representation. Okay, so that is why equivalent noise temperature is important. We replace the device with at the input side with some input resistance with the same and with equivalent temperature, such that at the output we have the same noise. Okay, so that is the effective is. And even more important parameter is called noise figure. I suppose you have gone through all this, just to go through once. Now what is noise figure? Noise figure actually characterizes the parameters or the characteristics of this noise characteristics of a device. How do you take this? So generally, obviously your signal input side, what you are getting, that will have some noise. Okay, let's say that is Ni. This is called Ni here. Input side already having some noise, but on top of that, this amplifier itself will have lead to some excess noise, which is called Ne, or excess or additional noise. So now both of them together, you will have some output noise. Okay, now noise factor is the ratio of SNR at the input side to the SNR at the output side. So remember this. This is very useful. SNR at the input side to the SNR at the output side of a device. So if you expand this, this comes to this. 1 plus Ne is the additional noise contributed by the amplifier, and G is the gain. Ni is the input gain. Okay. This is noise factor. So it will not have any unit. That means it is in linear scale. If you take in dB, that is by if you take noise factor of dB, then you get noise figure 10 log scale. 10 log f is the noise figure. Okay, so just remember this is the formula, and your for a source at 290 Kelvin, you will have some Ni. Ni is Ni is already generally for thermal noise you have KT not B, and noise figure you can calculate from this with the gain and all, right? So now we'll see how these are important for our calculation. So another thing is how do you make all this together? Is there any equivalent formula for calculating output noise figure, output noise total? So it says the noise factor formula is 1 plus Ne by Gni. Ne is the additional given by the device, and Gni is the gain and input noise. And total noise at the output No is Gni plus Ne. Obviously, it is amplified and added, right? Is this. Now, if you use both these formulas together, you get this. N naught is FGNI. Total noise at the output is multiplied by noise figure G and Ni. See, now you have to always remember this F is, when you multiply this, it will always become a noise factor, not a figure. In the calculation itself, these are all not log. Only when you will go to log, then it will become in dB scale, and you will tell is noise figure here. See, this is, if you take log of this, it will become like this. Log, it will become addition, right? Multiplication in log will become addition. So this is noise figure. Sorry, this is noise factor. But whereas this is noise in linear scale, which is factor. So this is just simple things. You just go through one. So this is how you can calculate total noise power here. But more important generally is the noise factor. Okay. So for our microstrip line, what is the calculation of noise figure? So it says if you have a this one. So the calculation is if you have a lossy transmission line at temperature T, what will be the calculation? So if you go through this and see the calculation, what is comes 1 plus L minus 1 by T naught, where this L is what? L is the loss, loss over the transmission line, of which is 1 over gain. 1 over gain is the L loss. Because if you have a loss across this, that means attenuation, so that will lead to some noise in your transmission line. Okay. So that is how you can calculate the noise factor for your device or a simple microstrip line. So now what happens at room temperature? This T is T naught, right? T naught is T. If you put that, F becomes L. So simply your noise figure becomes loss. Okay. So understand how it becomes. Your noise figure becomes a loss. If you just put T equals T naught, this is very simple formula but very useful also. If you have a lossy transmission line, then its noise figure becomes a loss together. Okay. Because minus 1 plus 1 gets crossed out, L becomes F. So that means if you have a 3 dB loss in your circuit, your noise figure will be 3. Simply that. If you have a lossless line, that means L equals 1, then your noise figure becomes, it will become simply 1. Okay. Okay, so there are calculation for passive networks and all. And for even mismatch also, it will lead to some losses. Okay. So because the mismatch, it will lead to losses, and again, it increases the noise vector in circuit. Now, another consideration is for passive components. Let's say the very simple Wilkinson power divider. And consider there is no loss. Is there any noise figure noise coming from that? Yes. Even without that also you get some loss in the circuit, and that is what leads to noise. Simple Wilkinson power divider here, if you see, if you calculate this formula, go by this, because it gets divided by 3 dB, right? Or half. So that's why whatever loss you have in your circuit, input to output, the same is your noise figure. Because it is 1 over 2, right? So that's why F becomes 2. Because your loss is 2, 3 dB means 2. That's why your noise figure here is because of this is 2. A quarter wave line section, the noise figure becomes 2 because it has 3 dB loss, because the power gets divided into two parts. Okay, these are the just simple formulas, and it might not be explicitly used in the amplifier, just to give you a brief overlook. And if you cascade, multiple devices together, as you know, the noise figure gets all added up like this formula. F1, F2, F3, and G1, G2 are the gain of this corresponding cascaded parameters. Okay. So what you see, F1 is the first one. The first stage noise figure is the mainly important. Okay. And the second stage and all, it is divided by G1, G2. So that reduces. But first stage, it does not get reduced. Okay. So that's why what you put in your device first stage, that will be accumulated all throughout. So you have to be very careful because of that. So now now for a amplifier, what happens? There are defined considerations for what are the sources. So because amplifier you can represent as a nonlinear device, it will have effective impedance and admittance, all these parameters, and it has some noise sources. Okay, which are multiple sources. Generally, you get into it has some source related noise. It has some source noise related to uncorrelated conductance, as well as due to equivalent noise resistance. So these are mainly three different considerations for or different sources for noise in an amplifier or BJT. So if you calculate from this, you get some effective noise figure. And from that, our task is to reduce this, right? So for this, there are some formulas, it takes some the partial derivative. And finally, to reduce this, you need some considerations and all. But all these are, not very important because these are mainly consideration for the designs. Okay, who design in the hardware level or the chip level is important for them. But because we are already taking a discrete transistor, in the datasheet only they will be mentioned. What will be mentioned? Manufacturers mentions minimum noise figure that can be achieved with the device. That is what is important for us. Datasheet will tell you what is the minimum noise figure you can get with this BJT or this MOSFET. And they tell corresponding input impedance, gamma, Y optimum or admittance, and corresponding reflection coefficient what you can get. And equivalent noise resistance and bias condition. These all you get from your datasheet. That is what is important for us, LNA design. So we'll take from there. Now, how do we incorporate into this? So far you remember, we are looking into only achieving some gain, some specific gain or a gain over some bandwidth. That is what we are designing. Now what we have to do, we want some gain as well as some noise figure. Both of them together we have to design. Okay. So what do we do now? Again, we go into Smith chart analysis. Similar to the stability circle we have seen, you have again a similar circle called noise figure circle or noise circle. Okay. So that circle again is defined by this. They have this circle also, it has some center and some radius. For calculating this, you need this parameter called n. How do you calculate? These are these factors. And that mainly, you need your desired noise figure as well as defined parameters which given in the data sheet. Just what we have talked about. First, you calculate this n. From that, you calculate the center and this radius. Okay. This will give you the parameters for your noise figure circle. You want some specific noise figure, which is f. For this, you have to calculate your center and radius. That we'll do now here. What do we do? See, what do we want? Some specific gain for this amplifier as well as some specific noise figure. So again, what we come back to is two circles. See the here, the violet circles are constant GS circle. They also have some center and some radius. That is, across this circle, they have, let's say, this one if you take, it is a 10 dB gain circle. Okay. For a 10 dB gain circle, all the points across this circle is 10 dB gain. And this left side, the red circle is constant X circle. That means for, let's say, 3 dB noise circle, noise figure circle. Okay. This is it. Now, when these two circles are, intersect, these points represent, you get 10 dB gain as well as 3 dB noise factor. That is what you have to come to. So finally boils down to you go to these parameters and again draw these two noise two circles. One is constant gain circle and another is constant noise figure circle. But never forget, we have already done the stability circle. That also comes into picture. We have already gone through that. After that, we are coming here. Okay. Now again we put this together, and the intersection of these two circles gives us the desired gain, possible optimum position for the noise figure as well as gain we want. That is how you have to design it. Okay, so this is nothing a big deal, just a design flow. You have to go one by one. So this is the whole process flow. Okay, first we select our transistor. The market, there will be lot of transistors available. How do you select? You see the what are the noise parameters you need, what is the power output required, what are the price, what is the layout, the how small it is. Then you choose a device, BJT, HMT, MOSFET, whatever. Okay. First you do K delta test. You see stable or unstable. If you are very lucky, then it might be stable. Then you go right direction. Okay. Mostly, but what you won't get there, you get a condition stable. So you calculate what is the maximum stable gain. Okay. Then you go to the once you calculate the matching using Smith chart, you remember the parameters or the stability circles we have drawn. From that we calculate gamma S and gamma L. That means from the source and load conditions we derive those. From that we design our matching section. So once matching is done,
Sir,
yes. Let me complete this, then
in
I will
that,
take questions. So
okay,
once
sir.
once the matching is done, then we'll see now plot the gain versus frequency and see if the stability is actually matching or done or not. We have seen match stability without adding matching. But now you have to see every step, you have to see stability is there or not. The moment you add this, you have to again do this. You are getting how much gain and how much stability. Okay. Once you do get this, now then next you have to look into the the noise figure part and see if you are getting your noise figure as well. So three things you have to get: noise figure, stability, as well as gain and matching. Okay. So all this step by step we'll do. Tomorrow we'll have a tutorial and look into this and the steps. Okay. We'll show you how to do this. And finally you have to do a layout. Obviously, once you do schematic, then you have the same thing. You have to go to a either you take a lumped component or a microstrip based circuit, go to layout, do co-simulation, and then check, verify everything together. So that is the whole process flow. Yeah. Yeah. Now ask questions. Yes.
Sir, in data sheet of power amplifier, where can we get this K stability parameter, sir? Which
I don't know.
parameter
I don't
tells
know.
the
Are you are
stability?
you are you following the this lecture or not? I don't know. First of all, I told a power amplifier I am not designing. We are talking about LNA here. And second, I showed you K delta is the calculation you have to do, not they have done. They will give you S parameters. I don't know. Are you
Sir,
listening properly or not?
In LNA also they won't provide any stability parameters, sir.
No, they won't provide. You have to calculate that. That's why, right? That's why we are studying all of this. You have to do it. They provide you S
Okay, sir.
parameter matrix. They provide
Yeah,
you S
they'll give
parameter
you.
matrix. From that, you have to calculate it. Yes. Anybody else?
Sir, actually, I have tried to do the assignment, but the results are not coming. Can you please check it? I will share my screen.
No, no. I can check it now. You do it yourself. I don't have time for that. So you have to do. As I told you, you start from the basics design. What I have shown. I guess you are talking about the energy harvesting circuit. Whatever I have
Yes, sir.
shown
Yes,
before,
sir.
first you do that, and then you go to that. Yeah.
Okay, sir. I have done the schematic, but the results are not coming
Yeah,
actually.
that is very much expected. You won't get fast result. It might take 1-2 more weeks. You have time. You can do it. Yes.
Okay,
Yes.
sir. Can you please extend the time of submission?
Yeah, yeah, that is possible. You do it. See, it is more like for your own learning only. Okay, you do it yourself. Yes, no problem. Yes.
Okay, sir. Actually, the I have done this it means I have done the schematic, but if you could check it, then it would be
No,
better
no, there, no, no.
actually.
See, for me, it's not. I don't have that much time to check for others also. You go through the first design what I've shown you. If you get there first, you understand from that, and then you go to this.
Okay, sir.
Any,
Okay.
any doubt on this class? Okay. So otherwise we'll stop here. We'll meet you tomorrow again.